Hi there, welcome back to our YouTube channel. We're going to look on torsion. Okay, let's say we're given a problem. As you can see, we have two shafts here, and we're going to have a pulley right here, A, B, and C, right? And we're going to be given the diameter of this shaft, which is 30 millimeters, and the diameter of this one is going to be 40 millimeters. So you can see my left hand shaft is bigger than the right hand shaft. Okay, and we're going to have a torque right here, which is acting in the counterclockwise direction, and also given the torque which is acting in the clockwise direction. So this one is the second, and the third is acting in the counterclockwise direction. Okay, and we're also given the length between two different pulleys. So we're going to have 1.2 from A to B and 1.8 from B to C. Okay, so T1 is the torque which is acting counterclockwise direction on point A, T2 torque on point B, and T3 torque on point C. Okay, we're given the value of the torque, which is 400 Newton meters. Remember, torque is measured as a moment. We're also given T2, T3, and you're given modulus material which was used to make the shaft. Okay, so we have questions here. The first question, I want to determine the maximum shear stress in the shaft AB and BC. I want to look on that. And number 2, I want to determine the angle of twist between AB and the angle of twist between A and C. So I'm going to just take a section between A and B. I'm going to take my section starting from the left hand direction. Okay, so if I take section right here, remember we still have the torque which is acting counterclockwise direction. Okay, and we're given the value of T1, we still have it. Okay, so that's what we're going to do. So let's just look at that section only. We're going to remove everything. We're just going to look at one thing at a time. This is the formula for shear stress. T stands for torque, right? And we're going to have R, which stands for radius, and IP is what we call the polar inertia. And we have the formula for the polar inertia. It's pi d to the power 4 over 32. If we're dealing with the radius, remember on 32 we're going to have 16, but in most cases we're just given the diameter. So that's why we deal with the d. Okay, so that's what we have. So now we have everything that we need. Okay, so let's go. On T, we're just going to put 400 Newton meters. R, we're just going to put 30 divided by 2. But remember to express everything in standard units. As you can see, the standard units for distance, it's meters. So it's going to be 15 times 10 to the power negative 3 meters. And IP, which is the polar inertia, it's pi d to the power 4 times 32. And the d of the diameter, but remember diameter is a millimeter, so we're going to change it to meters. Okay, and now it's a matter of substituting everything in our formula is what we're going to have. And we're going to have 75.5 megapascal. If you don't want to change anything to megapascal, you can just leave it in Newton meters and just write it 75, and mega, just remember, is 10 to the power 6, right? Now let's go to the next question and find the shear stress in the shaft BC. So remember the section that we're going to take. Now we're going to take the section between B and C, but C, we're going to consider the section between A and B, right? But in some cases, if I say you're under pressure, you can just take T3, right? And take that section. You're going to see if you take T3, it's going to give you the torque which is going to act in that shaft. But what we're going to do, we're just going to start from the left-hand section, and this is the section that we're going to take. Okay? Right? So here we have two opposite torque. We have the one which is acting in counterclockwise direction and the one which is acting in counterclockwise direction. Okay? So now let's just deal with it. So now we're going to have what we call resultant torque. Remember, these two torques are acting in different directions. So we're going to find the resultant torque. So since they're all acting in opposite direction, we're going to subtract. To find the resultant torque, we're going to say T2 minus T1, and that's going to be 1.2 minus 400, and we're going to get 800 Newton meters. And this is the same as T3, if you have noticed. Okay, now we still have our formula. We have everything that we need, right? Radius, we have the radius changing into standard units. So now it's a matter of substituting. And for the polar inertia, we're going to use the diameter. So what is the diameter that we're going to use? We're going to use the diameter in the second section, right? Not the one in the first section. Okay, right? So now let's substitute, and we're going to get 63.6 megapascal. You can leave the answer in Pascal or Newton meters, but I just change it to mega to simplify things, right? Okay, So this is what we have. And now I'm going to go to the next question. Determine the angle of twist between A and B and A and C. So what happened when torque is applied to a shaft? Okay, it is when torque is applied to a shaft, let's say we're going to have two different torque. So we're going to have what we call the angle of twist, right? Okay, so we're going to have two angles. So this is, let's say this is point C, this is point A, and that is point B, and this one is the angle of twist theta. Okay, and that one's going to be R, and we're going to have two opposite torque, right, as you can see, and we're going to have the distance. The angle of twist is going to be given by theta is equals to T for torque and L for the length, right, and G and IP, this one is the length of the shaft. So I'll show you a video to drive the angle of twist. Okay, so T is torque, G is the shear modulus, right, IP is the polar inertia, and L is the length. Okay, so from here we have T 400 Newton meters, we have L which is 1.2, we have G, and G were given it in the first page, that was 39 times 10 to the power 9 Newton meters. It was given in giga, right, in gigapascal, so just change it to Newton meters. Okay, IP is still the polar inertia, and we know the diameter of our shaft is 30 right here. Okay, so it's now a matter of substituting, as you can see, and if we do that, we're going to get our answer. And remember, our answer is radians. If you want to change this, you can just multiply by 360, and after that we're going to divide this answer by 2 pi. You can get the answer in radians. So this is going to be the answer. So what about the angle of twist between A and C? So remember, we have point A, which is on pole A, and pole C, but there's going to be two different angle of twist here. So just going to find the resultant angle, right? So that's what we're going to do. Okay, so let's find the angle of twist between B and C, and after that we're going to add it with the angle of twist between A and B. So still doing the same process that we have done previously. We have the torque, we have the length, right, and we have the shear modulus. So just a matter of substituting here. The only thing that have changed is the diameter, right? And if you do that, you're going to get our answer. And remember, our answer is in radian. And now that we have these two angles, you can now find the angle between A and C. We have calculated the angle between A and B and the angle between B and C. And the reason why I've put a negative sign on the angle between B and C is because I'm taking my moments in counterclockwise direction. So the angle between B and C will be in clockwise direction. So as you can see, that's what I've put it in a negative sign. But if we're asked to write the answer, remember it will be positive. So the angle between A and C is going to be the resultant between A and B and C. Okay, and if we do that, we're going to just substitute what we are given and don't round it off, right? Just going to round it off on the final answer. And if I want to change it to degrees, just multiply it by 360 and divided by 2 pi. So thank you for watching.